Good morning everyone. Today I am going to present experiment 3 sampling aliasing experiment reconstruction from digital communication laboratory. I have implemented this experiment using Python in Google Colab. The main purpose of this experiment is to understand sampling theorem, observe aliasing and reconstruct the sampled signal using sync interpolation. Experiment details. The experiment follows a complete process. First I generate a two-tone signal, then I physically sample it at different sampling frequencies. After sampling, I perform sync reconstruction. Finally, I calculate the reconstruction error, compare the signals in the frequency domain and calculate the aliased frequency for the undersampled case. Objectives. The main objective are to verify the sampling theorem using a two-tone signal and to test three different cases: sampling above, at and below Nyquist rate. Theory: sampling reconstruction. The continuous time signal used here is xt equals to sine of 2 pi f1t plus 0.5 sine of 2 pi f2t. In this experiment, f1 is 50 Hz and f2 is 120 Hz. So the maximum frequency present in the signal is 120 Hz. The physical sampling is represented as xn equals to x of nts, where ts is the sampling interval, ts is equals to 1 by fs. Here are the important equations of Nyquist condition. Fs must be greater than or equals to fmax. Here fmax is 120 Hz, so the Nyquist rate is 240 Hz. And the other three sampling frequencies selected therefore are for 400 Hz, 240 Hz and 180 Hz. Here is the system block diagram. First, the continuous two-tone signal is generated, then it goes through the physical sampler and produces sample section. These samples are passed to the sync interpolator to obtain the reconstructed signal. Finally, I compare the reference and reconstructed signals, calculate error and compare their spectra. Here is the algorithm or flowchart of the program, and here is the Python code of the program. I use a plotting resolution of 10 kilohertz. Again, this is only the numerical resolution for representing the continuous time waveform, and this is not the actual sampling rate. Sampling parameters. Here the continuous time signal is generated and the Nyquist rate calculated. Since the highest frequency is 120 Hz and Nyquist rate becomes 240 Hz, then I define the three physical sampling frequencies: 400, 240 and 180 Hz. Sampling function. This function performs the actual physical sampling for a given sampling frequency. It creates the sampling instance using Ts equals to 1 by Fs and calculates the signal values at those instants. Sync interpolation. Each sample is multiplied by a shifted sync function, and all these shifted sync functions are added together. This gives the reconstructed continuous time waveform. Spectrum function. Here I use the fast Fourier transform or FFT to obtain the frequency domain representation. The magnitude spectrum is calculated and only the positive frequency part is used for the comparison. Simulate all three sampling cases. Simulation and error. For each case, it generates physical samples. Reconstructs the signal using sinc interpolation and calculates the reconstruction error. Time domain plots. Now we come to the three time domain results. The first graph is 400 Hz, which is above the Nyquist rate. Here the reconstructed waveform follows the original waveform quite closely. The second graph is 240 Hz, exactly at the Nyquist rate. It is the theoretical boundary and is more sensitive to practical and finite duration effects. The third graph is 180 Hz, which is below the Nyquist rate. Here the sampling condition is violated, so aliasing occurs and the reconstruction is no longer represents the original signal correctly. The green stem represents the actual physical samples, while the continuous curve shows the original sinc reconstructed signals. Reconstruction error. These graphs show the reconstruction error for 400 Hz. The error is comparatively smaller. At 240 Hz, the error is more noticeable because we are exactly at theoretical limit. At 180 Hz, the error becomes significantly larger because Nyquist condition is violated and aliasing occurs. So the plots provide a direct numerical indication of the effect of sampling frequency. Frequency domain results. Now I compare the signals in the frequency domain. The original two-tone signal has frequency components at 50 Hz and 120 Hz. In the 400 Hz case, the sampled and reconstruction spectra preserve the components much more faithfully. At 240 Hz, we are the Nyquist boundary, but at 140 Hz, the spectrum shows frequency ambiguity because the 180 Hz component is undersampled. Alias frequency calculation. This is the most important calculation for the undersampled case. The sampling frequency is 180 Hz and the signal component is 120 Hz. So the aliased frequency is absolute value of 180 minus 120 equals to 60 Hz. Therefore, the original 120 Hz component appears as 60 Hz component after sampling. This demonstrates the main effect of aliasing. Error summary. These values provide a quantitative comparison between the original and reconstructed signals. Generally, when the sampling condition is violated, the reconstruction error becomes significantly larger. Here are the parameter table, and here are the time domain graphs. At 400 Hz, the samples are sufficiently dense and reconstruction is close to original. At 240 Hz, the system operates at theoretical boundary. At 180 Hz, the samples are insufficient to uniquely represent the highest frequency component, resulting in aliasing. Here are the reconstruction error graphs. The below Nyquist case has the most significant error because aliasing cannot be corrected simply by interpolation. And here are the frequency domain comparison. The original signal contains components at 50 and 120 Hz. For the below Nyquist rate, 120 Hz component becomes ambiguous and appears at the aliased frequency of 60 Hz. Observation. So we can also see that lower sampling frequencies mean fewer physical samples per cycle, and the reconstruction error becomes larger when the Nyquist condition is violated. Conclusion. To conclude, the sampling theorem was verified using a two-tone signal whose maximum frequency is 120 Hz. The Nyquist rate was found to be 240 Hz. At 400 Hz, the sampling is above Nyquist and reconstruction is substantially faithful. At 240 Hz, we operate at the theoretical Nyquist boundary. At 180 Hz, aliasing occurs and the 120 Hz component appears at 60 Hz. Thank you.